OK, so before the break, what we did, we started seeing that we can actually use partial fraction expansion as a useful way of dealing with higher order problems and reducing them to actually first and second order problems. Essentially, you can reduce it to the first order problems of complex conjugate forms or second order problems of real coefficients. But now there's one special case of it which we didn't talk about, and we would like to talk about. In all of the partial fraction analysis that we did, we assumed that the roots were independent and separate. There were no duplicates or multiple roots. They were not similar. They were different. So one question is that what happens when the roots are the same? You have multiple roots. So let's first think about the operator part of it, right? So if you have an h of p, the system operator operating on some function x of t, right? The question is, what if this h of p is of this form, p plus a to the m operating on x of t? What would this do? If you have, because this is when you have multiple roots, right? When you have multiple roots for the denominator, you will get this kind of form. So the question is, what does this do? Or what is this? So we can actually use the definition of this to find out what this looks like. So when you have multiple roots. So we can apply them one at a time. So you can say basically, this is p plus, apply them in sequence or in succession, right? So you can say, I can write this as 1 over p plus a to the m minus 1 operating on 1 over p operating on x of t. And then the question is, what is this? So now I can use the expression that we derived for this. We know what this does, right? It's e to the, it's the p plus a, yeah. E to the negative at, 1 over p, e to the at, u of t, right? That's what this does. Now if I apply the next one, take one more of these and apply, what do I get? What happens? So I get 1 over p plus a to the m minus 2 operating on 1 over p plus a operating on that. Operating on e to the negative at, 1 over p, e to the at, u of t. And now, but what is this when I operate this on this guy? Well, it's e to the negative, so let's expand it. 2, I get e to the negative at, 1 over p, e to the at, operating times this, right? But if when I multiply it, I get e to the negative at from here. 1 over p, e to the negative at, I'm sorry, positive at, u of t, or x of t, sorry, not u of t, x of t. These are all x of t. So this is general, not just for u of t, x of t. Right? But now this is where some simplification happens, because these two cancel each other. And every time you take one more of these, and apply it within this cancellation happens inside, right? So you can see that at this stage, you have 1 over p plus a to the m minus 2, e to the negative at, 1 over p squared, e to the at x of t. Right? This is where we are at this point. Now, every time I take one of these out, that inside e to the at will cancel this outside e to the negative at, and I get a p to the 3. Right? So at the end of this sequence, I will end up with e to the negative at, 1 over p to the m, e to the at x of t. Is this clear? If you're not convinced, you have to raise your hand. That this will keep happening, right? Every time I take one of these, it will have an e to the negative at up front. It will have an e to the at inside that will cancel this one. So then 1 over p would be right in front of 1 over p squared. So I will get 1 over p cubed. It keeps happening till you exhaust the supply of these, and you end up with m of these. Right? Make sense? Okay, so if I ask you what is the, for example, what is the impulse response of this system? P to the, okay, so let's make it even P plus A squared. If this is my h of P. So if I'm looking at the impulse response, I'm applying it on delta of T. It's 2. So I'm looking at the impulse response of a system, right? Which is h of P operating on delta of T, which is going to be, I'm saying that the system is 1 over P plus A squared on delta of T. So from this, what do we get? So according to this, this should be e to the negative at 1 over P squared of e to the at delta of T, right? So with the first integration, with the first 1 over P, well, for that one, I didn't need to worry about this. So because I get a 1 here, because this is times delta. Delta is 0 at all times except for T equals 0. So the value of this thing doesn't matter at all other times. So this becomes 1. So with the first P, I get e to the negative at 1 over P u of T, right? And with the second integration, I will get T e to the negative at u of T, which is exactly the response in case 2 when we were applying these in succession. You remember the critically damped system, which had where A was equal to B, which is shown as P plus A squared. Does that make sense? Now, the interesting thing is that in general, you can show that h of P plus R operating on x of T is equal to e to the negative RT h of P e to the RT x of T. So this is a more general expression. You say, well, how's this more general? Because if you assume that h of P is 1 over P to the m, right, then this becomes e to the RT 1 over P to the m e to the at, if you replace a with an r, x of t, which becomes this expression. And this side of it becomes 1 over P plus r to the m, which is this side of it. You can see that what we showed in black is a special case of what you have in purple when this happens. And you can express, this is easy to prove, it's like 3 lines. You need to write this as a Taylor series expansion, basically sorry, not a Taylor series expansion, as a partial fraction expansion, and write it as a sum of all those terms and apply these, and you will see that what you get is a partial fraction expansion of this. You can see it in the book too. Okay, so why is this useful? Because now what do we do when we have multiple roots? So let's say you have an h of P that has multiple roots. What do we do with that? So let's say you have an h of P that has a denominator of the form P plus A to the power of m. If you had something like this, what is the partial fraction expansion of that? What is the partial fraction expansion? Let's say just we start with something like that. In general, it could have some stuff in the numerator. Let's say. What is the form of the partial fraction expansion for this? Yes?
M times something over P plus A.
Times something. So is that sufficient? If I want to write it as partial fraction expansion, so if I have some stuff in the numerator, right? So if there's some n of P here, right? Would it be sufficient to have some, let's say, K m P plus A to the m? Is that sufficient? Can you express it this way? No, obviously not, right? What else do you need? Yeah?
You need to have all the powers of P plus A.
Exactly. You need to have all the powers of P plus A, right? In general. So this should be plus K m minus 1 P plus A to the m minus 1 all the way to, like, I don't know, K1 over P plus A plus some, well, that's it, I think, plus some function. Now, if it was in that form, then that would end essentially here. If it weren't in that form, in the more general case, if n of p, if it's a proper, so let's say if it's a proper fraction, then it will end there. If it's not, then there will be some function of p, right? Because if it's a higher order numerator, then first you have to do the long division, and you will get all these terms as like 1 plus p, 3p plus 5p squared, etc., etc. So those are all captured there. So assuming that you're only worried about this because you've done this beforehand, let's find out what these coefficients are. So how do I find the coefficient km? K sub m. How do we find that? If you use the previous trick. Can you think of a similar trick here? If I'm going to multiply h of p by something to get this coefficient for the coefficient km, k sub m, what should I multiply to just leave me with km? P plus m, yes, p plus a to the m, right? If I multiply it by that, what do I get? I get km plus km minus 1 p plus a plus next one over km minus 2 p plus a squared all the way to whatever, k1 times p plus a to the m minus 1 plus p plus a to the power of m f of p, etc., etc. Now, what is the value of this right-hand side if I set p to negative a? Yeah, yes, you have a question?
Yeah, it's a good question. Why do you include the m order p plus a? Because like wouldn't
This m?
no, in the very top. Yeah, like the first term.
Uh-huh.
Why is it the m order?
Why is it the mth order?
Why doesn't it start with m minus 1 basically? Because then wouldn't k of m just have to equal n of p?
So think about a specific example. Think about n of p being 1. Just the numerator being 1, unity. Can you express it in any other form? Right? You need that, right? You need that term. I mean, I'm giving you one example where that you need that term, right? So, yeah, that's technically all I need to do. If there's even one example where this, when you need it. I mean, yeah, so this is a more general term, right? You would need that term. Good? Because, you know, if you didn't have that term, if you wanted to express it in terms of the rest of them, you already have a common denominator among all of them. You will never need this common denominator of the mth order. You need a common denominator. Your highest order common denominator would be of order m minus 1. Make sense? Yeah. All right, good. No, good question. That's a good question. Any other questions? All right, good. So now, if you look at this and evaluate the whole thing for p, technically you should say being a minus 1, but I would just say p equals negative a. What would happen to these terms? I'm sorry, saying evaluating all of it, really. So there's like a bracket here. What is it going to be? What is this right-hand side if you set p to negative a? Km, right? All these terms will disappear because they at least have a p plus a in front. Does it make sense? So Km, so you can calculate Km, which basically this is equivalent to say also evaluate this for p being, I show it as negative a, this is not correct, meaning basically replace p with negative a because p is an operator, but I'm using notation loosely here. But you know what I mean. So in that case, Km, you can calculate Km. So Km is pretty straightforward. You just multiply the whole thing by p plus a to the m and evaluate it for negative a. So that's fine. How about Km minus 1? How do we calculate that one? Oh, you have a question? Yeah, go. Oh, you want to say the next one? It's okay. Go ahead. Yeah.
So you would
So you're saying subtract this from that
So,
and then divide by p plus a?
to the n minus, well, yeah, basically.
Yeah.
So,
You could do that, but practically it may be hard. You could do that. So that's another way of doing it. So what you're suggesting is actually interesting. So she says that, look, subtract, you have calculated this, right? You have an expression here. Before you set it to negative a, just take this expression. Once you found km, subtract km from this. So it would be you're subtracting you're starting with a rational function, some polynomial divided by some polynomial minus some constant km. So it would become a new polynomial divided by the denominator, which would be the same. And then you say, do the same thing, but now this time instead of with m to the p plus a to the m, do p plus a to the m minus 1. You could do those kind of things, but it becomes very complicated when you go down the road. There's an alternative way of doing this. The alternative way of doing it is interesting, because think about what happens if before I just do this evaluation, if I calculate the derivative of this thing with respect to p. What is the derivative? So let's write it in a different color. So if I take this and do the derivative with respect to p of that. Now this, to the m, right, this guy, is this, right? This whole big expression. So I can calculate what is the derivative of this thing with respect to p? So what is the derivative of this with respect to p? Constant, 0, right? So what is the derivative of this with respect to p? Km minus 1. What is the derivative of this one with respect to p? Some 2 km minus 2 p plus a, right? And the next ones over would be like, I don't know, 3 km minus 3 p plus a to the square, etc., right? So all the subsequent ones will have a p plus a in them, at least, to some power. Yes?
Aren't you multiplying by p if you do d, if you differentiate them?
Sorry, with respect to p. Yeah. So this wasn't the derivative with respect to p. I just wrote it the wrong way. Yes. That was a smart way of saying it. Okay, that was a fun way to say it. Okay, good. So now, if I evaluate this function or this expression for p being negative a, what do I get? What do I get now? Again, this is not correct notation. I should say replace p with negative a, but so we'll handle it, right? So what do I get? Km minus 1. And in general, Km minus I is 1 over I factorial d to the I dpi, or let's write it as n. I is too loaded in our course. Of p plus a to the m h of p. Evaluated at, this thing evaluated for p equals negative a. That's what it is. Yes?
Can we not simplify people say to the n h of p as just n of p?
N of p, capital N of p? Yeah, you could, but so that's basically what you're doing, right? That's what you're doing. You're evaluating N of p, but you don't know what N of p is in general. If you know it, you could write it as N of p. True. But you may have other terms in the denominator where you can actually do this. So it's not limited to this. So in fact, this is also generally true, and you can see everything applies if you had some additional terms, let's say Q of P here. Because you could make all of these arguments again. So this is generally true, not limited to this particular specific case. I just showed it as a starting point, right? Because you can separate those denominators into their own fractional expansions, and you will end up with this part. Okay. So this looks pretty complicated, but actually in practice it's pretty simple when you start doing it. So let's do an example to see how it's applied. Actually, it makes it a lot easier because you get rid of a lot of terms. So this is a very simple example. So let's say you have a current source, Is of t, that drives a capacitor, a resistor, and an inductor. So the capacitor, the resistor is, let's say, 0.5 ohm. Capacitor is 1/4 of an ohm, and inductor is 1/4 of an ohm. And they're looking at that. So the question is, for example, what is the impulse response of this thing? So we are looking at the impulse response, h of t. So we need to find a system transfer characteristic. Now, in this case, the system transfer characteristic, or transfer operator, or system operator, is what kind of an operator? It operates on a current, it produces a voltage. What do we call those? Things that take a current as an input and produce a voltage as the output. They're generalizations of resistors, impedances, right? So these are Z's. So it's a Z of P operating on Is of t, producing V of t. And if we think about it, then it's easier actually to calculate the inverse operator, which would be the Y of P, operating on V of t, generating Is of t. Now, in this case, it's simple because if you do think about Y, it's just a parallel combination of these three reactances, which is the sum of those reactances, right? R, Cp, 1 over R, Cp, and 1 over Lp, are the reactances. So you have 3 parallel resistors, right? Think about 3 parallel resistors. You can treat them as conductors, right? If you have 3 parallel conductors, what do you do? What is the overall conductance? What is it? It's the sum of the 3 conductances, right? So now Y's, their admittances, are the general form of conductances, right? So you can combine the 3 of them. So you can say Yp is essentially what? 1 over R, which is 2, plus Cp, which is 1/4 of, so 1 over 4p, plus 1 over Lp. It's like 1/4, so it's like 4p. I'm sorry. This is p over 4, and this is 4p. 4 over p. Think about this. This is 1 over R. This is Cp, right? Yeah, 1/4 of p. And then this is 1 over Lp, which is 4 over p. Yes?
Should it be a 1/4 farad?
Yes, yes, they are.
You wrote ohms on everything.
Oh, yeah. Oh, okay, sorry. Thank you. No, this is an error. Thank you. Any others? Yes?
For that thing you wrote in blue, like, why is it okay to say P equals -8 for some things but not other things?
No, it's not for some things. It's for all things.
Oh, excuse me.
No, or maybe I didn't understand the question. Sorry. So you're talking about this, right?
Yeah, anything right above it too. So there you were using the assumption that P equals -8.
Uh-huh.
And then when you write the thing in blue, you don't treat P as -8?
No, I calculate the derivative first, then apply this. Because if I apply this, it's like when you calculate the derivative at 0, right? Derivative of a function. Let's say f of x is x squared. If I say what is the derivative of this function at x equals 0? I don't go and plug 0 in here first and say, well, okay, it's 0, then the derivative of 0 is 0. Well, in this case, actually, it is. So let's make it x cubed. So let's say x cubed, right? Okay, you know what? Let's just say x. That's even simpler, right? If I say x, no, this is not 0. The derivative is not 0. So if I plug 0 here, no, this is correct. Right? So if I put 0 here first, what do I get? I can't say f of 0 is 0 and then derivative of this thing therefore is 0, right? I have to calculate the derivative first and then apply 0 to it. So the derivative of this thing is 1, and then I evaluate it for x equals 0, which gives me 1. Therefore, the derivative of this function at x equals 0 is 1. The slope is 1 here, not 0. The same thing is happening here. So you have to calculate the derivative first at that point, and then you evaluate it at that point. Right? Make sense? Good. Any other questions? Okay. Now, so this is backwards of what I wanted, right? What I want is 1 over this, which is fine. So it's basically then really what I'm looking at is v of t is inverse of this thing, which is basically the inverse operator. But we know this behave like rational functions. So it's 1 over 2 plus p over 4 plus 4 over p times is of t. So this is now the impedance operator. So now I can simplify this a little bit. I can say, okay, well, multiply by p, so I get p over p, and multiply by 4p to make life easier. P squared here plus 16, okay, plus 8p plus 16, operating on is of t. Right? It's just the same function, just simplified it. Right? So now I have to do partial fraction expansion. So if I want to do partial fraction expansion of this thing, what are the roots of the denominator? 4 and negative 4 and negative 4, right? So the denominator can be factored as p plus 4 squared, and the numerator is 4p is of t. So now I'm doing a partial fraction expansion on this one. So I have to write it as something over p plus 4 squared plus or minus something over p plus 4, both of them operating on this is of t. So what are those somethings? Well, let's find these coefficients. So how did we find this first coefficients? Who's next in line, I guess? Jennifer. What was the procedure? What was the process? Yeah, I know. So you take this, what was the way? You multiplied it by, this is m, right?
Oh, okay, yeah.
Oh, okay.
So 1 over 2, like, I'm looking at the pink thing.
Just yeah, you can use, you're using this, right?
Oh, okay.
For the first one. P plus, so what do you do? Multiply this. This is your h of p. You multiply by what?
Oh, okay. I multiply by p plus 4 squared.
P plus 4 squared, right? Which basically gets rid of this. And then evaluate it for what? For p equals to what?
P equals
Negative 4, right?
Oh, yeah. Yeah.
So what is it?
Negative 16.
Negative 16. So this is negative 16. It's actually an easy calculation. It looks difficult, but it's an easy calculation because it just basically gets rid of all of that stuff. So how about the next one? What you just calculated is that thing. So you don't need to recalculate this every time. This basically just leaves you with 4p. So this product is just 4p because you've already multiplied it by p plus 4 to the m, right? So this is 4p. Then what do? The first derivative of 4p is 4. Right? This is the thing. You have to build up the understanding, but once you do it, it makes it easy to do. That was the bad news part you asked me about earlier. Right? If you know how to apply it, it's actually very simple. So that's it. That's the partial fraction expansion of this thing. So now if I ask you what is the impulse response of this thing, so therefore, well, h of t is going to be this thing, 4 over p plus 4 minus 16 over p plus 4 squared, operating on delta of t. Now, since you've been working on that, tell us what this impulse response is. What's the first part? For e to the negative. Right. So what's the second one? We did these. Okay, 16, yes. You remember how we did this, right? A couple different ways, right? Let me just see if I can pull it down here. Or where was it? I did it somewhere as an example. Did I? Oh, anyway, so this is the response, I mean, from what? So it's 16t, negative 4t, u of t. Exactly. So you can write it as 4e to the negative 4t times 1 minus 4t u of t. That's the response. Yeah. The more common way of writing is actually to order it this way. Okay? Make sense? All right. So now we know how to do these things, right? I mean, we know how to deal with all different kinds of these things. And now the key part happens next, which is what we're going to do in the next lecture. And listen to it because so you can anticipate it. So we will come up with a way to describe all our inputs also in these terms. We'll generate all of our possible inputs off of an impulse using an operator. And then we don't need to worry about these things because then we'll form a catalog of what kind of forms correspond to what kind of responses. And since we can do this partial fraction expansion, there are not that many forms. And once you know the response for that, you know the response to any rational function. And therefore, if you have that catalog of like 7 or 8 items, and if you know it, then you know the response to any input. So you don't need to do any of these integrations anyway. You can just basically look at it, do a partial fraction expansion, and tell me what the response is. All right. Any questions? All right, well, see you next time.